Next chapter, chapter 7, linear programming. In Form 2, we looked at solutions of simultaneous linear inequalities in which by drawing suitable straight lines and shading off one side of each line, we ended up with the required region. This region is also called the feasible region, and it satisfies all the inequalities simultaneously. Linear programming is a method used to find the best solution to problems that can be expressed in terms of linear equations or inequalities. The solutions are usually found by drawing graphs of inequalities and looking for optimum values that satisfy the required conditions. Let's see how we form linear inequalities. Given a statement of condition, you can be able to form an inequality to represent it. For example, to proceed to the next class, a student must attain at least 500 marks. Suppose x represents the number of marks, then we could say x is greater or equal to 500. That is the condition to proceed to the next class. This inequality will produce a straight line. In linear programming, we often have several conditions, meaning we have several inequalities which we represent in a graph. For example, Ben goes shopping for pens and pencils. He has 200 shillings in his pocket. A pen costs 20 shillings and a pencil 15 shillings. Taking the number of pens to be x and that of pencils to be y, let us form inequalities to represent this information. The first thing to note is that Ben cannot buy negative number of items. So the first inequalities are x is greater or equal to 0 and y is greater or equal to 0. This means that either he buys something or nothing, but he can't buy a negative, though he can choose to buy nothing, that is 0. Next inequality. Ben cannot spend more money than he has. Whatever number of each item he chooses to buy, he will spend either all the 200 shillings or less. And therefore, given that each pen costs 20 shillings, if he buys x number of pens, that will give us 20x plus each pencil costs 15 shillings. If he buys y number of pencils, we shall have 15y, and that should be less or equal to 200. These inequalities are called constraints. They are basically restrictions or conditions. X and Y are called decision variables. They tell us what quantity to buy, sell, produce or transport, and so on. These two are called the non-negativity constraints because we are dealing with real-life situations. There could be certain conditions that would rule out the non-negativity constraints. For example, suppose Ben wants to buy at least 3 pens and not more than 4 pencils. Then we'd have x is greater or equal to 3 and y is less or equal to 4. This will effectively take away the non-negativity constraints. Next, graphical solutions of inequalities. After forming the inequalities, the next step is to represent them on a graph, get the feasible region, and find all the possible combinations of items to be purchased. For example, Alice went shopping for pens and pencils with 60 shillings. A pen cost 15 shillings and a pencil 10 shillings. Represent this information and find all the possible combination of items she can purchase. In our solution, first we form the inequalities. Let x represent the number of pens and y the number of pencils. First, she does not have conditions for the minimum number of each item she can buy, and so we automatically have the non-negativity constraints. X is greater or equal to 0 and y is greater or equal to 0. Secondly, whatever combination she buys, she cannot spend more than 60 shillings. Remember, x and y represent the number of items to be bought. We have the price for each item. X pence at 15 shillings makes it 15x, plus Y pencils at 10 shillings make it 10Y. That must be less or equal to 60. This simplifies to 3x plus 2y is less or equal to 12. These are the three inequalities. We plot them as lines, assuming the inequality sign is an equal sign. So we have the line x is equal to 0, which is basically the y-axis, and y is equal to 0, which is basically the x-axis. The lines are continuous because the inequality is a greater or equal to. Even without taking a test point, we know that we shall shade the negative sides. The next line, 3x plus 2y is equal to 12. We get 2 points. When x is 0, y will be 6. So the first point is 0, 6. When y is 0, x will be 4. So the other point is 4, 0. The line is continuous as well. But which side do we shade? We take any point and test if it satisfies the inequality. We take 1, 1. Substitute that in the inequality. 3 times 1 plus 2 times 1 must be less or equal to 12. 3 plus 2 is less or equal to 12, and 5 is less or equal to 12, which is true. So we shade the other side of the point 1, 1. So this is the feasible region and represents all the possible combinations of what Alice can purchase. We take all the points in that region, including on the lines, because they are continuous. But remember, only take whole numbers or integral values. Starting at the corners, we have 0, 0, which means he buys nothing. 0, 6, which means he buys 0 pens and 6 pencils. 4, 0, meaning she buys 4 pens and no pencil. We also have 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, 1, 0, 2, 0, 3, 0, 1, 1, 2, 1, 3, 1, 4, 1, 2, 2, 2, 3, and 3, 1. These are all the possible combinations. Another example, 150 people are to be transported using a matatu and a minibus. The matatu can carry a maximum of 15 people per trip and the minibus 25. The total number of trips must not be more than 7. Taking X for the number of matatu trips and Y for the number of trips by the minibus, represent this information on a graph. So let's have the inequalities. First, neither the matatu nor the minibus can make negative trips, and so X must be greater or equal to 0 and Y must be greater or equal to 0. Total number of trips must be equal or less than 7, and so X plus Y must be less or equal to 7. Again, all the 150 people must be transported. So whatever number of trips will be made, the number of people transported must be 150 or more. So the inequality for the total number of people will be 15x plus 25y must be greater or equal to 150. That simplifies to 3x plus 5y is greater or equal to 30. So these are the constraints. We plot the lines on a graph. If we take test points for each line and shade off the unwanted sides, this is the feasible region. The points within this region are the solutions. From this, you can be able to pick all the possible combinations. So that now we move to optimization. Optimization is the process of finding the ordered pairs of variables that give the maximum or minimum values for a given expression. These ordered pairs of variables are found in the region that satisfies all the inequalities. The process of finding the maximum and the minimum values of linear functions under limiting conditions or constraints is called linear programming. The expression to be optimized is called the objective function. How do we come up with the objective function? Let's go back to the first question. We have the constraints for Alice shopping of pens and pencils. Suppose Alice buys the pens and pencils to go and sell at her shop at a profit. And let's say that a pen sells at a profit of 6 shillings and a pencil a profit of 5 shillings. What combination of her purchase will yield the maximum or the minimum profit? In this case, we need to form the expression for the profit. Each pen makes a profit of 6 shillings and they are x pens. Therefore, we have 6x plus each pencil makes a profit of 5 shillings, and so y pencils will have a profit of 5y. So our objective function is 6x plus 5y. Sometimes we represent it with z. So we say z is equal to 6x plus 5y. This is the function we need to optimize, meaning we find the minimum and the maximum values. The maximum and minimum combinations are found at the points of intersection of the lines or the corner points. If the point of intersection is not an integral value, then we take the point closest to that corner. We then substitute the coordinates in the objective function and see which corner yields the maximum or minimum value, whichever we are interested in. Let's name our corners 1, 2, and 3. At corner 1, the coordinates are 0, 6. Substituting in the objective function, we shall have 6 times 0 plus 5 times 6, giving us 30. At corner 2, the coordinates are 4, 0. Substituting in the objective function, we have 6 times 4 plus 5 times 0, giving us 24. Corner 3, the coordinates are 0, 0. If we substitute, we end up with 0. So the maximum profit will be achieved at the point 0, 6, and that is equal to 30 shillings. The minimum will be at 0, 0. Of course, if she buys nothing, she should make no profit. Let's form an objective function for the transport question. Now, suppose the matatu is paid 2,000 shillings per trip and the minibus 3,500 shillings per trip. Which combination will be most cost effective? In other words, we find the minimum point. We form an expression for the objective function. 2,000x, the cost of the matatu, plus 3,500y, the cost of the minibus. So we optimize this function, that is minimization. We take the corners and let's number them 1, 2, and 3. At corner 1, the coordinates are 0, 7. If we substitute in the objective function, we shall have 2,000 times 0 plus 3,500 times 7, giving us 24,500. At corner 2, the coordinates are 0, 6. If we substitute that, we get 2,000 times 0 plus 3,500 times 6, giving us 21,000. Now, the coordinates of corner 3 have decimals, and because we are dealing with a real-life situation, we cannot select it. Obviously, because we cannot have a fraction of a trip, like half a trip. What we normally do is pick the nearest point to that corner, but within the feasible region and with a whole number coordinates. Looks like that point will be 0.16. We number it 4. What will be the cost here? We substitute in the objective function. 2,000 times 1 plus 3,500 times 6 will give us 23,000. Looking at all the three corners, the most cost-effective approach will be at point 2, and that will cost 21,000 shillings. Let's take one more example. We want to maximize the expression 2x plus 5y using the extreme or corner points approach. What we have here is a linear programming model. We have the x and y, which we call the decision variables, and that they tell us what quantities to buy, sell, transport, and so on. The 2x plus 5y is the objective function, which we want to maximize. These two are the constraints or restrictions on how to attain the objective. We can label them C1 and C2. These two are the non-negativity constraints. To solve these, as usual, we first find the points for the lines that satisfy the constraints. For C1, when x is 0, y will be 8, and when y is 0, x is 16. For the second constraint, when x is 0, y will be 15, and when y is 0, x will be 9. Now, when drawing the graphs, you realize we stay in the first quadrant, where x and y are both positive because of the non-negativity constraints. For the first constraint, we have the points 0, 8 and 16, 0. That's the line. For the second constraint, we have the points 0, 15 and 9, 0, and that's the line. If you do the test points and shade off the unwanted region for each line, this will be the feasible region. From here, the optimal solutions occur at the extreme points or at the corners. We label them 1 to 4. The maximum solution will occur at one of them at least. To decide which one is optimal, we will find the coordinates of each point, substitute in the objective function, and choose which one is the best. At point 1, we have 0, 0. Point 2, 0, 8. Point 3, 9, 0. And point 3, 6, 5. Now we determine the optimal point by getting the corner point that will give the highest value for the objective function. We want to maximize the objective function z equal to 2x plus 5y. At point 1, we have 0, 0, and if we substitute in the objective function, it gives us 2 times 0 plus 5 times 0, which is equal to 0. At point 2, we have 0, 8, and so the objective function value will be equal to 2 times 0 plus 5 times 8, giving us 40. At point 3, 6, 5, z will be equal to 2 times 6 plus 5 times 5, giving us 37. And at point 4, 9, 0, z will be equal to 2 times 9 plus 5 times 0, giving us 18. There we have it. Point 2 provides the highest value of the objective function, and so the solution occurs at point 2, which is the maximum optimal point. If you wanted the minimum optimal point, that would be point 1. Now we look at another optimization method, the objective function search line approach. So far, we have used trial and error method in determining the minimum and maximum optimal points for the objective function. An alternative method is to use a search line. Let's learn this method by way of an example. In this example, we will solve this minimization of the objective function 5x plus 7y. We start by drawing lines for the constraints. For the first constraint, when x is equal to 0, y will be equal to 2, and when y is 0, x is 6. For the second constraint, when x is 0, y is 5, and when y is 0, x is 2. For the third constraint, y is always 4, irrespective of the value of x. Again, when choosing the coordinates, try and limit them to the first quadrant, where x and y are both positive. For the first constraint, we have the points 0, 2 and 6, 0. We join the 2 and form a line. For the second constraint, we have points 0, 5 and 2, 0. We join them and form the line. For y is less or equal to 4, the line is simply at y is equal to 4. If you take the test point for each line and shade off the unwanted region, you will have this as the feasible region. Now, we know that the optimal solution for this region will occur at the extreme or corner positions. Let's label them A, B, and C. Now, recall our objective is to minimize 5x plus 7y. So we find the corner point that will give us the minimum value of 5x plus 7y. Instead of testing each point separately, we will use a search line. To get a search line, we equate our objective function to a k, where k is any number, but preferably the LCM of the constants of x and y. In this case, k will be the LCM of 5 and 7, and that will be 35. So now we have the equation of 5x plus 7y is equal to 35. This will be the equation of our search line. We plot that line. Get 2 points. When x is 0, y will be 5. And when y is 0, x will be 7. So the search line is this blue dotted line. Now, when we want a minimization solution, we move the search line downwards towards the origin 0, 0, parallel to itself. If it's a maximum solution, we move the search line upwards away from the origin parallel to itself. The last point that the line touches before leaving the feasible region is the optimal solution point. So let's move the search line downwards parallel to itself. So you can see it passes points A and C, and obviously point B is the optimal solution. As you will notice, the coordinates of point B are not whole numbers. When dealing with real-life situations and objects that do not take fractional values, such coordinates would not be correct. What we do is take the last point with whole number coordinates that the search line touched. If you take the line backwards, that point will be 3, 1. To get the optimal function value, we substitute the coordinates of this point into the objective function 5x plus 7y. So we shall have 5 times 3 plus 7 times 1, giving us 22. But if the items can take fractional values, then we proceed with the true optimal point. For example, in our case, we do not know what the constraints and the objective functions represent, and therefore if we assume they can take fractional values, we shall find the optimal value at point B. But first, we need to know the coordinates of point B. We solve the green and the red lines simultaneously. Here are the equations, so let's solve them by substitution. From C1, we rewrite x in terms of y. We have x is equal to 6 minus 3y. Then we substitute this into C2. That gives us 30 minus 15y plus 2y is equal to 10. That becomes minus 13y is equal to minus 20, and y is equal to 1.5. If we substitute the value of y here, we shall have x is equal to 6 minus 3 times 1.54. That gives us x is equal to 1.38. And so these are the coordinates at point B. If we substitute them into the objective function, we shall have 5 times 1.38 plus 7 times 1.54, giving us 17.7. And you will see the value is less than the 22 we calculated using the closest point. Always take note of situations that don't take fraction of values and take the point nearest to the extreme point. One last example. In this example, we will solve this maximization problem using the search line approach. This is the objective function and these are the constraints. We start by finding points on the line satisfying each of the constraints. For the first constraint, when x is 0, y is negative 3, and when y is 0, x will be 0.43. These 2 points are not friendly to work with. We have a negative and a quite difficult decimal. We don't want this, so let's try some more points. To make it easier to find useful points, let's rewrite the equation in terms of y. Y is equal to 7x minus 3. We can use try and error to find better points. When x is 0.5, y will be 0.5. And when x is 1, y will be 4. For the second constraint, we have minus 3x plus 6y is equal to 10. When x is 0, y is 1.67. And when y is 0, x is minus 3.33. Again, the points will be difficult to locate on the graph paper. Rewriting the equation, we have 6y is equal to 10 plus 3x. So y is equal to 10 plus 3x over 6. When x is 1, y will be 2.17. When x is 2, y will be 2.67. So it looks like we can't get whole numbers for this one. So let's be happy with that. Third constraint, 3x plus 4y is 9. When x is 0, y will be 2.25. And when y is 0, x is 3. Let's try one more point. When x is 1, y is 1.5. That's better. Lastly, C4, 3x plus 3y is 3. When x is 0, y will be 1. And when y is 0, x will be 1. That's simple. The non-negativity constraints are simply the x and y axis. For the first constraint, we can just plot the last 2 points, 0.5.5 and 1.4. That's the line. For the second constraint, we use the first and the last 2 points for accuracy, and that is the line. Third constraint, we use 3, 0 and 1, 1.5, and that's the line. For the last constraint, we have 1, 0 and 0, 1, and that is the line. If you do the test point for each line and shade of the unwanted region, this would be the feasible region. To determine which of these extreme points is the maximum, we draw a search line. We want to maximize negative 3x plus 12y. We equate it to a k, which is the LCM of 3 and 12. That will be 12. So we have minus 3x plus 12 is equal to 12. We draw that line. When x is 0, y will be 1, and when y is 0, x will be negative 4. Because of this negative 4, which is not in my graph, let's have one more point. When x is 2, y will be 1.5. Using these 2 points, the search line is this one. Because this is a maximization process, we move the search line upwards away from 0 parallel to itself to obtain the maximum optimal point. It shows that the maximum solution occurs here at the intersection of constraint line 2 and 3. It's a fractional intersection point. We can get the coordinates by simultaneously solving equations 2 and 3. These are the equations. We use elimination because the coefficients of x are 3 and minus 3. If we add the two equations, we will eliminate x. Minus 3x plus 3x is equal to 0. 6y plus 4y is equal to 10. 10 plus 9 is 19. Y is equal to 1.9. Substituting that in 3, we have 3x plus 4 times 1.9 is equal to 9. 3x is equal to 1.4 and x is equal to 0.47. So the optimal solution is x is equal to 0.47, y is equal to 1.9. Substituting that in the objective function gives us 21.4. If the problem involved items that can't take fractional values, then we would have to find whole number points nearest to the optimal corner. In fact, in our case, there's only one such point, 0, 1. And so in summary, in linear programming, conditions are expressed as linear inequalities and are called constraints. These are then represented on a graph. The optimal solutions lie in any of the corner points of the feasible region and are called extreme points. The optimal solution could be a minimum or maximum. By using test method for each corner or drawing a suitable search line, you can be able to identify the required optimal point.
If you want to go on and major in math or do honors in math or do a career in math, you really do need to be good at it. But I think too many people stop out too soon because they've had bad experiences. I think math teachers have a lot of responsibility for that. We haven't taught it so well. We haven't provided the resources that people need. And so I think if you need help, you need to get it, and you need to get it early. And you need to work at it.